Avete qualche domanda prima di fare altri esempi? Vorrei fare una piccola correzione nell'esempio che abbiamo fatto prima con 3 città. Let us switch to English and say, okay, we started to record the second part of our lecture of 24/11, and the small correction is connected with the example of our 3 towns. Therefore, we turn back to our discrete example of variabile aleatoria in italiano or random variable in English. Let us turn our example before going to continuous probabilities. Our example was connected with 3 towns example. So we had 3 towns, x1, x2, x3, and we said our goal is to find good shoes. Therefore, the question was, what is probability to find the best probability to find the good shoes in our 3 cities? How we can find these best shoes? And therefore, we can say that this purpose to find best shoes in these 3 towns for us shall be kind of random variable. Therefore, when you have a random variable, you are saying, the purpose is to find shoes in one of 3 cities. Or you can change your desire and say, I want to find shoes that have longer lifespan, so they can be used for a longer period. Or you can say, I want to buy cheaper shoes. Or if you have enough money, you can say, I want to buy most expensive shoes. Of course, this is also kind of purpose. In each 4 cases, we have 4 different random variables. Why? First random variable to find a shoes, not one shoes, we said our random variable should be determined when we go to the town x1. Said probability to find shoes here was 1/3. Probability of x2 was 1/6, and then we found the last probability to find a shoes for in the town 3, 1/2. Therefore, if you have random variable, therefore something that you take from the real life, and you say, this is my purpose, then for each random variable, you define these probability densities. And you define probability this random variable x. For example, probability for my, let us call this x random variable, x to be in the set x1, x2. How we can find? This, of course, can be found on the basis of our definition of these probability densities. whenever we have our random variable, we have this um, function. In this case, these are three values, P1, P2, P3, such that, as we said, the sum is 1. For example, if I want to find the two shoes, what is probability to find the shoes in the first two towns, not in the third? For this, we can say that this set is union, this joint union of these guys. So this probability is 1 over 3 plus 1 over 6. So this is 1 over 2. Therefore, what I didn't underline before the break and now want to underline, a very important remark, is that each random variable has his distributional densities such that when we take the sum in discrete case or integral in the continuous case, totally, when you integrate probability density or take the probability density, the result is always 1. And if we change the random variable, then suppose we have another random variable. Random variable, this means for this random variable, we have to define what is the probability density associated with this random variable. For example, if we have other random variable, say for our case, that is to find shoes with longer lifespan, we have to say, if you find, if you make your choice in town X1, what is probability to have at least 10 years? And then you have some probability for this set, P1. Then you have to say, what is probability to find shoes in the second town, such that the lifespan is bigger than 10 years? And you have the second, P2, and then you define P3 as complement of P1 and P2, because you need all the sum to be 1. And then you say, for my variable, for my random variable, I have density, which is the following, and we make the same list of probability density associated with this random variable. Similar thing we can say about the continuous case. We set that in the continuous case, our example is a random variable with equidistributed density. This random variable such that our P of X was defined as 1 over B minus A for any X belonging to interval AB. So this was our definition of the probability density. Probability density is a constant, and then if we want to measure what is, for example, probability of our set, for example, alpha beta, or sometimes this is written in the following way: probability that our random variable belongs to alpha beta set. This is simply integral. This is equal to the integral from alpha and beta of our function probability density dx. So my random variable, that is defined from real life problem, my random variable, in order to have no sense of distributional to have sense of random variable, will have corresponding density defined in a proper way, such that instead of sum to be 1, we have integral from a to b dpx dx. This is 1. So probability density is non-negative function between 0 and 1, and integral shall be 1. Similar to the discrete case where we have the sum. And in this case, when you take this integral, the result is you take your function, take 1 over b minus a, and then here you have beta minus alpha. When you integrate your probability density, this is the constant I put in front, and then integral from alpha to beta gives you beta minus alpha. Therefore, for equidistributed functions, the situation is very simple. Let us consider another example of another random variable with another density. But before going and before cleaning these two examples, let me ask you if you have some questions connected with these two examples of probability densities.
Professore, scusi, nell'integrale cerchiato che va da A a B, che cosa c'è scritto accanto all'integrale?
So this is our x. Let me write it above so that you can see better. I shall write this above. I have to change also this black. We have integral from a to b, px dx. This integral is exactly 1. Okay. Some other questions? Let us work on another example, another random variable with different density. Okay. Example 3. Suppose you take data of some statistics. For example, we have the following distribution between the day 0 and the day, how to say, n. We have for n days the data of distribution of kind of a virus. And suppose your graphic is the following. Your statistical data shows that the development of the virus and the number of infected persons for this is the time, and this is number of infected persons, this is t, 0 day, 1 day, and so on. Here is the maximum. These are segments. Of course, it is better to put this midpoint kappa, so n shall be 2 kappa, and we can try to find, for example, let us suppose that kappa is 4, and this maximum is, let us make this in thousands of people. Let's say here 6,000 people. What is the graphic of this function? And the question is, if this is our function ft, what you can say about your probability density? Therefore, if we want to make random variable, we want to say that our probability density should be very similar to this picture from the real life data. Therefore, how we shall, this is kind of our modeling process. So we want to choose in such a way, and this function, first of all, we shall make this function. For example, if this is 4, I think it is better to take here 4 because the equations shall be more simple. When kappa is 4, what is n? 2 kappa, so this is 8. What is the, let's call this point A, this point B? Of course, B has coordinates 8, 0, while the point A has coordinates 4, 4. What is the graphic, what is the for our OA segment? It is clear that our ft is t for t between 0 and 4. Let me write bigger, so more clear. This is t for t between 0 and 4. So this is dependence is 45 degrees, and this function is exactly 4 is ft equal t. What we can say about an, at t equal 4, this shall be 4. At t equal 8, this shall be 0. So probably we can take t. This should be negative 8 minus t. Why we take this function? You see, this is linear function with pendance 1, and this is with pendance minus 1, what is corresponding to our graphic. And this shows t between 4 and 8. Sorry, 8 is this, not infinity. We can say our function p of t, before we set p function of x, but if you have a function of x or function in t, this is the same. Our probability space, in order to have the model, the better model, we can say our omega, the domain where the function is our random variable is, shall be the interval, we take omega to be interval from 0 to 8. Our random variable will have probability density similar to this one. So in our model, we can say P of T, let be constant multiplied by this function ft that we already defined between 0 and 8. For t, 0 and 8. Now the question is, what is the precise value of c so that your probability density shall have similar structure thanks to this constant c? And this shall be our probability density associated with this random variable, that is random variable evaluating the spread of the virus, number of people, that what is probability that in the moment, for example, 5, the person shall be infected. So probability shall be this random variable, probability that the person is infected in some day of the interval in time that we studied. This random variable will have probability density. Usual natural function that is probability density associated with this random variable shall be constant by this function. And now we can define in the same way as we define the constant for the case of equi-distributional probability density, we can define this constant. So we have to check that integral from 0 to 8 of pt dt is 1. This is the condition that is absolutely necessary to be probability density. Now we put inside this quantity constant integral from 0 to 8 of our function ft dt. Of course, our function has two formulas. One is from 0 to 4, is from 4 to 8. Therefore, we shall divide our interval into disjoint intervals in order to compute this. So we need 1 to be equal to this, and this shall be equal to constant integral from 0 to 4, and then what is between 0 and 4? Our function is t dt plus c, or if you prefer, we can put here brackets, plus then we have integral from 4 to 8. And what is the definition of the function according to our modeling process? This is 8 minus t. You can compute this integral, but since I know very well the geometrical meaning of the integral, geometrical meaning is the area of the part of the plane below my graphic. So this triangle OAB. So this is C by the area of a triangle OAB. I put absolute value to remind us that this is the area. But the area of this triangle is the base by the altitude divided by 2. Altitude is 4, the base is 8, divided by 2. This gives C times 16. And now you can find your constant, because we asked C by D be 1. This one was 16. You can correct me. Do you agree? So I have 4 by 16. And therefore, from here, we can compute our C is 1 over 16. And now we can say that our probability density, of course, this is a very rough approximation of the real data, in this case shall be with probability density defined in such a way. We can define finally PT. This is, as we said, 1 over 16 times T when T is in 0, 4, and 1 over 16, 8 minus T in the interval between 4 and 8. With this in hand, we have our random variable that has this probability density. So you can see this example and ask me if you have some questions or some remarks. Actually, here to finish my lecture, I can pose 2-3 examples that you can, probably 1-2 examples that you can try to solve. Small problems. Problem 1, you can try omega is 0,2. Our probability density is constant x to the power 3. You can try to find the constant c such that probability density of random variable, so the calculation is similar. Or you can try to find probability of, this is more omega, is interval 0 infinity. This is not very real life problem, but formally you can take omega to infinity, and you can take px equal constant 1 over 1 plus x squared. Try to find c. As you can see, all these problems to find probability density, they are connected always with calculation of some integrals, some basic integrals of first course of analysis. So I am planning to stop here, and if you have some questions, observations, we can discuss now or leave some questions for the next appointment tomorrow. Okay, so we can continue tomorrow. Thank you for your attention. I shall stop the recording.